morning to all. Today we have to discuss about oxidation states of d block elements. When we comparison oxidation states of d block elements, s block elements, p block elements, d block elements shows variable oxidation states. What is the reason? Because small atomic size and having vacant orbitals. Due to small atomic size and having vacant orbitals, d block elements shows variable oxidation states. Okay, now for suppose we have to discuss about oxidation states of 3D series. Right, scandium only shows +3, titanium +2, +3, +4 in this +4 stable, vanadium +1, +2, +3, +4, +5, +5 stable, and +2 also stable only, but +5 more stable. Chromium +2, +3, +4, +5, +6, +3 stable, and also +6 stable. Manganese +2, +2, +3, +4, +5, +6, +7, +2 stable, +2 stable. Next +7 also stable, +7 also stable. Next iron +2, +3, +4, +6, okay, +3 stable, +3 stable. Cobalt +2, +3, +4, up to +4 only cobalt. Okay, 3d7 +4 stable, and +2 also stable only somewhat, +4 stable. Right. Next nickel +2, +3, +4, +2 stable, +2 stable. Cobalt +2 also stable somewhat, +2 also stable only. Next copper +2, zinc +2. This is the variable oxidation states in 3D series. Okay, then we have to discuss how does these transition elements react with different electronegative elements. Okay, first react with halogens. React with halogens. First about fluorine. Fluorine react with transition elements formation higher oxidation compounds. That means CrF6, MnO3F, here +7, here +6. Okay, next VF5, here +5, like that. Fluorine react with transition elements to formation stable higher oxidation states. What is another reason is fluorine has more electronegative element. That's why it can form stable higher oxidation states. Then another reason why fluorine form higher oxidation state means maybe high lattice energy, because fluorine is small atomic size also. That's why lattice energy inversely proportional to radius. Small atomic size means more lattice energy. So fluorine formation higher oxidation states with transition elements. If ionic compounds means if ionic bonds, if ionic compounds means, okay, cobalt hexafluoride, that is due to lattice energy. Otherwise, if covalent compounds means, for example, CrF6, chromium hexafluoride, due to high bond enthalpy. That's why due to high bond enthalpy, it can form high oxidation state covalent compounds formation. Due to lattice energy, so fluorine can form with transition element high oxidation state ionic compounds. The next one, but fluorine unstable in lower oxidation state. Very important point. Fluorine unstable in lower oxidation states. Okay, for example, vanadium, VX2, like that compounds. Okay, that's why fluorine more stable compounds formation in higher oxidation states only. Okay, so fluorine unstable in lower oxidation state compounds. Okay, that is the important point. Next, chlorine, bromine, common. But among halogens, fluorine only form higher oxidation state compounds with transition elements. +6, +7, only fluorine formation. Chlorine, bromine, maximum up to +5 oxidation state only. Then another one, CuX. Here Cu +2 stable, CuX. Here X means fluorine, chlorine and bromine. Okay. So here iodine, important point. Iodine does not give CuX. That means CuI does not exist. What is the reason? Because Cu2 plus oxidize I minus 2 I2. Cu2 plus oxidize I minus 2 I2. That's why CuI does not exist. Okay. Next, FeCl3, FeBr3 exist, but FeI3 does not exist. FeI3 does not exist. What is the reason? Here iron 3 plus oxidize, answer, iron 3 plus oxidize I minus 2 I2, or I minus reduce due to this reason, FeCl3, FeBr3 exist, but FeI3 does not exist. Right. Next, with oxygen. Oxygen also more after fluorine, periodic table, after fluorine, oxygen has more electronegative element. That's why with oxygen also transition element shows higher oxidation state compounds formation. So, for example, Mn2O7 plus 7 oxidation state, MnO4 minus, okay, here also plus 7. Next, CrO4 2 minus plus 6. Next, osmium tetroxide plus 8. Next, ruthenium tetroxide plus 8. Okay, that's why lower oxidation state of the formation compared to fluorine also, oxygen only form higher oxidation state with the transition elements, that is plus 8 and plus 7. Fluorine has maximum up to plus 6 oxidation state compounds formation. Fluorine maximum up to plus 6 stable oxidation compounds formation, but oxygen plus 7 and plus 8, plus 7 plus 8 oxidation state compounds also formation. That's why in totally oxygen only can formation with transition elements higher oxidation state compounds. That oxidation state is plus 7 and plus 8. That's why higher oxidation state given by osmium tetroxide plus 8 comma ruthenium tetroxide plus 8. So 3D series manganese give with oxygen plus 7, 4D series ruthenium give plus 8. Next 5D series osmium give plus 8 oxidation state. Okay. Then oxygen can form lower oxidation states. Oxygen can form lower oxidation state compounds also formation with the transition elements. For example, that is CuO plus 2, ZnO plus 2, Cu2O plus 1. Okay, next VO2 plus 4, Sc2 scandium, discandium trioxide, Sc2O3 plus 3, V2O3 plus 3, Cr2O3 plus 3. Next, MnO2 plus 4, V2O5 plus 5, Fe2O3 plus 3, cobalt oxide plus 2, dicobalt trioxide plus 3, like that. So different MnO2 plus 4, okay, Mn2O3 plus 3. So oxygen can form different oxidation compounds with transition elements. In lower oxidation state also stable, in higher oxidation state also stable, and in average middle of the oxidation state plus 3 plus 4 plus 5. In middle of the oxidation state also stable, but fluorine only stable in higher oxidation states with transition elements to form compounds. But in lower oxidation state, fluorine has unstable. But oxygen is formation in all oxidation states, stable compounds with transition elements. Okay. Then there are another important one. Oxidation state increases means oxidation state increases. Oxidation state increases. Oxidizing power increases. Oxidizing power means gain of the electron. It can able to gain of the electron. Oxidizing power increases. Okay, that means oxidizing power directly proportional to higher oxidation state. Oxidation state. Next, generally in lower oxidation states, act as a reducing agents. Act as a reducing agent. That is +1, +2, +3. Here in higher oxidation state, act as a oxidizing agents. In higher oxidation states, act as a oxidizing agents. Oxidizing power same. Reducing agent, reducing power same. Act as a oxidizing agents. Okay, that is +5, +6, +7. This point is important, very important. So transition elements in higher oxidation states like +5, +6, +7 act as a oxidizing agent. Oxidizing power is more. Transition elements in lower oxidation states like +1, +2, +3 act as a reducing agent. That means reducing power is more. That's why this point you should remember. Next one. When the oxidation state increases, acidic character increases. That means transition elements in higher oxidation state, they have acidic behavior. In lower oxidation states, they have basic behavior. Average +4, +3, +4, +5 like that means they have amphoteric nature. That's why +1, +2, that should be basic character, whether oxides or fluorides or any halides. Basic character. +1, +2 should be basic character. Examples: ZNO, Cu2O, CuO, vanadium oxide. Okay. Next, +3, +3 may basic character or amphoteric nature. Amphoteric +3 character, whether basic character or amphoteric Next, the vanadium oxide also come. Titanium Ti2O3 plus 3. This is basic. Then exception Cr2O3 plus 3, but this is amphoteric nature. Amphoteric nature. So, should remember plus 1 plus 2 conformly basic character any compound. Plus 1 oxidation state, plus 2 oxidation state oxides compulsory basic character. Plus 3 somewhat basic character some compound shows amphoteric character. For example, scandium titanium shows basic character, but chromium oxide shows amphoteric nature. This is next. Plus 5 plus 6 plus 7 shows acidic character. Acidic character. Plus 5 plus 6 plus 7 oxidation shows acidic character. That is MnO4 minus plus 7, CrO4 2 minus plus 6, like that. Then exception vanadium pentoxide plus 5. So vanadium pentoxide although having plus 5 oxidation state, but it shows amphoteric nature. Amphoteric nature. So this is about the acidic character. Its stable higher oxidation state, maximum acidic character. One compound exception, vanadium pentoxide. Except vanadium pentoxide, all plus 5 oxidation state, plus 6 oxidation state, plus 7 oxidation state oxides having acidic behavior or acidic character. So simple remember amma, in higher oxidation states, plus 5, plus 6, plus 7, these elements having acidic character and act as a oxidizing agents. In lower oxidation states, plus 1, plus 2, plus 3, 1 or 2 exception leave that, plus 1, plus 2, plus 3, these are act as a reducing agent as well as having basic character. Reducing agent, basic character in lower oxidation state, oxidizing power and acidic character in higher oxidation states. Generally plus 3 plus 4. Plus 3 plus 4 oxidation states, they act as a amphoteric nature. Plus 3 plus 4, they act as a amphoteric nature. But some exceptions is there. Some exceptions is there. This is about the acidic character and basic character and amphoteric nature of oxides of transition elements. Next, these transition elements shows zero oxidation state also. Right. Zero oxidation state also. Zero oxidation state also. Right. For example, nickel tetracarbonyl. Here, nickel oxidation state 0. Nickel oxidation state 0 because coordination chemistry you understand now. Because this is neutral ligand. Neutral ligand. Neutral ligand. Next, FeCO4 is also due to this one neutral ligand. Next one, some important points. Cr3 plus more stable than Cr4 plus Y. Cr3 plus means so 3D5 4s1 amma chromium 3D5 4s1 here 1 here 2 3 electrons lose. That's why this is D3. Cr4 plus means so 1 and here 1 gone, here 4 gone. This is 1 2 D3. Okay, this is D2. Okay, D3 state more stable in aqueous solution. That's why D3 more stable than D2 in aqueous solution. That's why Cr3 plus more stable than Cr4 plus. On previous question came Cr3 plus stable than Cr2 plus in aqueous solution. Why? Cr3 plus means so D3, correct na? Cr2 plus means D4. Okay, now only I explain. In aqueous solution, D3 more stable than D4. In aqueous solution, D3 more stable than D4. That's why Cr3 plus more stable than Cr2 plus. Next one, like that question. Next, manganese 2 plus more stable than manganese 3 plus. Why? Manganese 2 plus means 3D5, manganese 3 plus means D4. So D5 is the off-field stable. Due to Hund's rule, according to Hund's rule, off-field subshell is very stable. D maximum electrons 10. 5 means off-field. 5 means off-field. That's why according to Hund's rule, off-field subshell is stable. This is D4. That's why stable off-field filling of D subshell. That's why Mn2 plus more stable than Mn3 plus. Then generally nickel always stable state +2. Then nickel 4 plus. Next, platinum always +4 oxidation state stable than +2 oxidation states due to their ionization energy values. Okay, this is the variable oxidation states in transition elements. Next one, another one, important one. Along the period, higher oxidation state stability decreases. The 3D or 4D or 5D series, any series across the period from left to right, higher oxidation stability decreases. Higher oxidation state stability decreases. Then in groups top to bottom, higher oxidation stability increases. In groups top to bottom, in group top to bottom, higher oxidation state stability increases. Okay, that means 3D to 4D, 4D to 5D. So 3D to 4D, 4D to 5D. So stability increases. Higher oxidation state stability increases. Okay. So this part is very important. Again, listen. Across the period from left to right, higher oxidation state stability decreases. Next, in group top to bottom, in a group top to bottom, higher oxidation state stability increases. So 3D to 4D, 4D to 5D, higher oxidation state stability increases. This is about the variable oxidation states in transition elements.